Okay, hi guys, so we'll be continuing on seeing more on calculation of work done. So let's get started. So suppose we have a case wherein we see a gaseous reaction in which we see that A moles of A reacts with B moles of B and converts itself into C moles of C. Okay, so change in volume or delta V in this case would be equals to C times Vm C minus A times molar volume of A, this is capital C, minus B times molar volume of reactant B. Okay, so delta V can be written as C minus A minus B times Vm. Okay, so we can write that this is delta Ng, and what is Vm? Vm is volume per number of moles, so that would be equals to RT upon P. Okay, that should be equals to delta V. Okay, so how are we writing that this C times Vm of C minus A times Vm of A minus B times Vm of B would be equals to C minus A minus B times Vm. So let's look at like this, that what is the final volume, which is final volume of the gases which is present in the vessel. So final volume would be, let's suppose you have been given molar volume of C, so final volume would be molar volume of C times C. Why can we write this? Because we know that total volume divided by moles of C, which would be equals to molar volume of C. So now we have been given the molar volume of C, so total volume would be C times Vm of C. Similarly, what would the volume of the vessel before the reaction, or in other words when gases A and B are present? So volume occupied by A would be molar volume of, rather volume occupied by 1 mole of A would be V upon A. Similarly, volume occupied by 1 mole of B would be V dash upon B, and total volume in this case would be V plus V dash, that would be AVM plus BVM of A and B. Okay, so with this we can write that it would be nothing but the initial volume would be A times molar volume of A and B times molar volume of B, and what is the final volume? Final volume would be C times molar volume of C. Okay, and then we can write that the change in volume would be C minus A minus B times Vm, and Vm can be written as what is the molar volume of, after the reaction gets over, molar volume can be written as RT upon P. So just substituting this value. Okay, so let's suppose we have an example that a solid X gets converted into Xg. So let's suppose 1 mole of Xg gets converted into Xs converted into Xg, so we can write delta Ng would be equals to 1 in this case, and W would be equals to minus 1 RT. Okay, so this is W is nothing but delta Ng RT. Okay, why is this the case? Because we can say that W equals to minus P external delta V, and delta V can be written as delta Ng RT upon P. P and P gets cancelled, so we can write W would be equals to minus delta Ng RT. Okay, delta Ng would be positive in this case, positive 1, because number of moles of gaseous products minus number of moles of gaseous reactants, or stoichiometric coefficient, would be 1 minus 0. Okay, but in this case, let's suppose we have X of solid gets converted into X of liquid, then we have to calculate delta V would be equals to V of XL minus V of XS. So W in this case would be minus P external delta V. This has to be separately calculated, and W equals to minus delta NGRT formula won't work in this case. Okay, next let us see isothermal process. So what is the work done in isothermal process? So isothermal process means simply dT equals to 0 or temperature equals to constant. Okay, so we can write that du would be equals to dq plus dw. This we already know. So for an ideal gas, we can write that u is a function of temperature only. We already know this. So as u is just a function of temperature, and as temperature is not changing, so change in internal energy would also be 0. So du delta u would be 0, delta h would be 0. Why? Because both are functions of just temperature in case of ideal gas. Okay, so we can write dw plus dq would be equals to 0. In other words, we can say that work done plus heat exchange would be equals to 0. Okay, so let's say heat is provided onto the system, so this will lead to expansion. This was our initial system. There were some gas molecules here. Now heat is provided. This would result in expansion of the gas molecules. As a result, delta V would be positive, hence work done would be negative. This is one of the scenarios. And another scenario can be, what about the gas is getting compressed? So if the gas is getting compressed, so then we can write that delta V would be negative, and this would be a case of compression, and this boundary would be shifting downwards and heat would be released. Okay, so in this case we can write that heat absorbed by the system is equals to work done by the system. Heat absorbed by the system would be equals to work done by the system. And in this case we can write that work done on the system would be equals to heat released by the system. Okay, next let us see the isothermal ideal gas expansion and compression. So we would be seeing isothermal ideal gas expansion compression. So let us first see reversible process. Okay, so for reversible process we can write that P external would be equals to P internal plus minus dP. Okay, so we can write that dW would be equals to minus P external times dV, and dW would be equals to minus, just putting the value of P external as P internal plus minus dP here, so we will get P internal dP or dV minus plus dP times dV. Okay, so as this is the multiplication of two very negligible terms or two negligible terms, so this would be very negligible term. Okay, so we would be getting dws minus nRT upon V times dV. Okay, just putting the value of P internal. Okay, so just again integrating it. So we would be getting that W reversible would be equals to, so W reversible would be equals to minus nRT ln V2 upon V1. Okay, so we can also write it as so in this case we assume that P internal would be equals to pressure of gas, that would be equals to nRT upon V. Okay, so here we can also write that it would be equals to minus 2.303 nRT log V2 upon V1. Okay, and we can also see that as P is inversely proportional to V, so we can also write it as minus 2.303 nRT log P1 upon P2. Okay, next let us see the graph of the same. So suppose we have a graph of P and V, and the gas is going from point A to point B. Okay, so from state P1 V1 to state P2 V2. Okay, so work done from A to B is simply gas expansion. Okay, and work done from B to A, let's say after the state of the gas comes from A to B, let's say it again goes from B to A, so work done from B to A would be considered as gas compression. Okay, and we can write that WT would be equals to, as it is a reversible process, we can write that WAB plus WBA would be equals to 0. And how can we write that? Because let's suppose W from A to B or work done from AB can be written as minus nRT ln V2 upon V1, and work done from B to A again can be written as, so let us write that only. So suppose work done from A to B can be written as minus nRT ln, what is this is VB or V2 upon V1. Okay, and work done from B to A would be again minus nRT ln, what is the final volume here? It is again going from B to A, so final volume would be V1 upon V2. This is isotherm, as the heading itself says that we are calculating the work done for the isothermal ideal gas expansion or compression. Okay, so VAB, and this is VAB and this is VBA. So we can see that this can be written as nothing but nRT ln V2 upon V1, just adjusting the minus sign here and taking it inside the logarithmic factor. So WAB plus WBA would be equals to minus nRT ln V2 upon V1 plus nRT ln V2 upon V1, that would be equals to 0. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing the same for the irreversible process. So till then, good luck and goodbye.